Alright, so here's the graph of this function. Would you have guessed it was a line?
No.
No, why not? Okay, yes for somebody, no. Why yes?
Oh, I said no.
Oh, who said yes? Okay, who said no? Why? Why would you not have guessed it was a line?
Because it's a rational equation.
It's a rational, absolutely, so you would have guessed more of the,
The plan. Yep.
right? Okay. Why else?
It has x squared.
Has an x squared in it, sure, yep.
Just looks complicated.
This looks complicated, so sure as heck ain't going to be a simple line, right? Okay, alright, sure.
What you said.
That's very common sense, especially with where we're at right now. Okay, now let me show you why it's a line. Okay? Do you recall factoring? What times what gives you x squared? X times x. What two numbers multiply to negative 33 and add to 8? Positive 11 and then negative 3, right? Those are the two factors that would multiply together to get this quadratic trinomial. Okay? Factor the top for me.
7 negative 4.
Parker?
7 negative 4.
So x plus
7.
7 and x minus 4, right? Okay? So my two factors, if I were to factor the top, if I were to break it down into two binomial factors, I got an x plus 7 times an x minus 4. If I have x plus 7 times x minus 4 divided by x plus 7, what happens? X plus 7's cancel out and you're left with what? X minus 4. What does the graph y equals x minus 4 look like? A line with a slope of 1 and a y-intercept of negative 4, right? That is why the graph then looked like it did right here. The y-intercept was negative 4, it had a slope of 1. However, very good, it cannot, we know it can't hit negative 7. So it's not this nice continuous line. It looks like it on our graphing calculator, but that says the graphing calculator goes down to really tiny decimal places and we can't even see the hole that would be there. However, if I go to table, which is right above graph, so here's a table of values for this graph, what do you notice when x is negative 7? Error message. Again, I went to table, so I went second graph, and I went to table, and it's this XY chart that the calculator makes for you. Okay? So, yeah, exactly. I'll show you here in a second. And then you can see all the different Y values for specific X values, and you'll notice at negative 7, there's an error. Yes?
How'd you get used to do that? Because when I click my table, it just brings up like a table I use for
You hit second graph,
There's an error.
right here.
Oh, here we go.
It's
We're
an
good now.
error.
Never mind. We're good.
Okay? Alright, so what we really have going here on our graph, I'll pull it back up, is you can't see it because, again, we draw the hole fairly big to make it obvious. But what we really have back here at negative 7 is we have a little hole in that graph. Okay? So it really looks something like this. That's really what this graph looks like. There's a hole in it when x equals negative 7. Because there is no y value when x equals negative 7. Because if you try plugging in a negative 7 for x, you get error, right? You get undefined because you cannot divide by 0. Yes? You with me on that? So in this case, there is going to be a hole at negative 7. So how do you know when there's going to be a hole in the graph versus how do you know when there's going to be a vertical asymptote in the graph? Yesterday's graph had a vertical asymptote, right? What did I have you guys write down in your notes about when there is a vertical asymptote? Okay, it approaches but never touches, but how even without the graph could I tell? What else did I write?
Value makes the denominator zero.
What value of x makes the denominator equal 0, right? If you look closely at this one, -7, that makes the denominator equal 0, but what does it also do to the numerator? Makes it equal to 0. So if you have an x value that makes both the numerator and the denominator equal 0, there's going to be a hole in the graph and not a vertical asymptote. Vertical asymptotes occur when the denominator equals 0. Holes occur when both the numerator and the denominator equals 0. Okay? Holes occur when the numerator and denominator equals 0. So can everybody see how in this one, an x value of -7 would make both the numerator and the denominator equal 0?
Yeah.
So therefore, this function will have a hole at x equals -7. Will this function have a vertical asymptote?
No.
No, because there is not a value that only makes the denominator equal to 0. So this function has no vertical asymptotes.
Did you have more than one vertical asymptote?
Yes, you can. The question was, can you have more than one vertical asymptote? Actually, somebody asked me that the other day. Here would be a function that has more than one vertical asymptote. This says, how can you read that over there as a glare bad?
Yeah, 8.
8 over the quantity x minus 1 times x plus 6. An x value of 1 would make my denominator equal 0. So there's a vertical asymptote at x equals 1. An x value of -6 would also make my denominator equal 0. Therefore, at x equals -6, there is also a vertical asymptote. And those values didn't make the numerator equal 0. So in this case, this one would have 2 vertical asymptotes at x equals 1 and at x equals -6. Can a graph have a vertical asymptote and a hole? You bet. Okay? It can have multiples of each or none. Just depends how many factors, really, in a sense, that a function has. Okay? Any questions, difference between holes and vertical asymptotes right now? Okay? I'm gonna come back to this one here, because we gotta finish what yet? We gotta do range, and we gotta do discontinuous versus continuous, right? Okay, I'm gonna come back to this, but I just wanna make sure you kind of understand the holes and vertical asymptote part. Let's say I had some crazy function whose factors are this. Does this function have any holes?
Yes.
Yes, where?
That does.
X equals -6? Because wouldn't -6 make both the top of this and the bottom of this equal to 0? So that would have a hole at x equals -6. Would it have any vertical asymptotes?
No.
Yeah, where?
5.
At x equals 5, because wouldn't a 5 make the denominator equal 0? Okay, and there's one other one. 0. Wouldn't a 0, if x equals 0, right here, if x is 0, wouldn't that make my denominator equal 0? So this one has 2 vertical asymptotes at x equals 5 and x equals 0, and it has a hole at x equals -6. Tell me where we're at, difference between where holes are located and vertical asymptotes are located in functions. I'm going to take silence as a good. No questions? Okay. I'm going to go back to this. We got to hit our range and we got to hit our continuity, right? Range, I've kind of said you can look at the graph for the range. So here's my graph. But remember there's a hole in it right there, right? So range, what y values does this graph hit? All of them except, whatever the y value is right there. What is the y value right there? Looks like negative 11. Can you explain why? You're right. Can you explain why this looks like it? Or are you just saying, that seems like that would be the pattern? You're looking at the table?
Yep.
Okay. So she's saying, from her table of values, if you look at the pattern here, well, that's a negative 12, that's a negative 10, so, I mean, common sense says negative 11, right?
Yep.
All right. I like that thought. I can prove it to you why it's negative 11. Can anybody else see why it would be negative 11 without just looking at the pattern?
Because like a regular linear function would be 7, 7, but then when you subtract 4 it'd be 11, or add 4 would be 11.
These two parts cancel each other out, right? And all we have is x minus 4. We have y equals x minus 4. If you plug negative 7 in for x, what do you get for y? Negative 11. So if your function was simply just y equals x minus 4 and you plugged in negative 7 for x, out would come negative 11 for y, so you'd have the coordinate negative 7 comma negative 11. But why isn't that coordinate actually on this graph? What? There's a hole at negative 7. It can't go through that point. If I try to plug negative 7 into the actual function, okay, you'll get an error message. But that one location where there is a hole, okay, that hole is located at negative 7 comma negative 11. That is where the hole is located because y equals x minus 4, and if I plug in a negative 7 for x, what do you get for y? Negative 11, right? So that means that this graph touches every y value except what? Negative 11. So what is my range going to be? Good.
If I do that U with a little, I'm not this.
You want to make it a U with the tail?
Yeah.
It's okay, you can. But questions on range? All right, and then continuous or not continuous? It's not continuous, right? How could you describe it? Point discontinuity. And therefore it is removable. And I will go ahead and tell you on your test, I'm going to actually ask you what you would have to do to make it continuous. Fill it in, right? Okay. To make it continuous, let y equals negative 11 when x equals negative 7.
Oh.
You could just write something like that. Basically, we are assigning y a specific value when x equals negative 7. Even though negative 7 was not in the domain of the original, if we wanted to make it a piecewise function, we could make this function continuous by simply just adding this coordinate. Okay? So, the two that I've done for you are probably about as difficult as they're going to be. There might be a couple more more complicated ones, but some of them are going to be very easy. Okay? for the next few minutes here, we're going to do a couple together, all right? Or you're going to do them, and then we'll talk about it. We're going to do a simple one here, y equals x plus 5 cubed, and then we're going to do a piecewise one, okay? So, let's start with this one. Find the domain, the range, if there are any vertical asymptotes, holes, and talk about its continuity.